You should be able to see that just fine. Oh, you have to be kidding me.
We might have had both, but I remember one used for 25 questions.
You have to be. Sorry. That's it. All right. All right, so this is TGO 6.16. So first of all, let me ask, does anybody have any questions about anything from last lecture? I ran all the way back to my office to get my version of the notes with this image, and then somehow it sent the wrong file. Awesome. So anyway, so here's what's going on here. I'm recording right. This is the virtual memory access flow. So you start out with a virtual page number, right? So what's going on is you are doing a load word calculation. You've calculated your address, and it's trying to indicate, we know that from last lecture, we have this page offset and a location within the page. So that becomes our 32-bit calculation, right? So that's what's coming out here. So first thing we do is we go to this page table that contains this valid bit first, and then the correlation between where the page is in the page table and the actual physical memory. So these are actually another level of pointer, kind of like how you have in cache memory, you had an instance here where you were pointing to a cache block by using the offset, right? Recall that? So that's kind of the same concept here, except the page table is going to tell you the virtual page memory. It tells you the size of the page offset, and it tells you where to go in the page table. Page table then says, all right, I can relate to physical memory. If it's not there, let's say I have a valid bit and my valid bit is 0, well then that's when I actually start going to disk storage. So then what's going to happen is you get the page from the disk storage, you go to the physical memory, if you recall from last lecture, kind of the diagram for the operating system, and then you update the page table to indicate that this would point to that. Yes, Alex?
The page table is in main memory too?
Yes, the physical memory. Yes?
Is the disk storage the same thing as the virtual memory?
No. Virtual memory is the concept of using the physical memory as a cache. Right. So then the disk storage are the actual disks, that the drums that we were talking about, where this is the slowest portion of the memory hierarchy. And but what's going to happen is a virtual page number would go here to the page table, look up the location in physical memory, and then if I wanted this page, then I could swap it into the cache hierarchy and then I could put in the local registers I need into the data path.
So virtual memory isn't really a physical thing, it's just really a concept of using the physical.
Correct. That's exactly right. Virtual memory is a concept. All right, so this is a general idea. So in there you have the virtual page number, you have a page table which contains the physical or disk addresses. Each one contains a valid bit, and then if it's in there, if it's valid, it's going to point to this physical memory, which is where your concept of using virtual memory comes in. Or if it's not, if it's invalid, it goes to the actual disk storage itself. And this is 6.16. All right, so skipping over that. All right, so now we're kind of in this place where we're going to start talking about multiprocessing. So this is the last major concept we're going to go over here in this class. So you've kind of heard of multiprocessors, you've heard of multi-cores, you have the general idea that those exist, right? So up to this point, we started out the fundamental concepts in digital design, then we started talking about arithmetic, we went to an arithmetic logic unit, we learned how registers work, we learned how memory addressing works within a data path, we then learned the full data path design, and then we learned how can we get things in pipelining, right? So we try to improve the process even more. So now we're trying to improve the speed and the throughput of the processor even more, try to improve the performance. We're going to start out with this idea of multiprocessing. How do I use multiple processors to accomplish tasks so I can increase the flow? So we formally define the multiprocessor as a computer system with two or more processors. The objective of running a multiprocessor is connecting multiple computers to get higher performance. So we're now even going further into this higher performance execution of compiled code. And just like when we introduced pipelining into the data path, trying to do multiprocessors has multiple issues. So one thing you can do is, instead of using a large inefficient processor, kind of like a very large instruction word or a complex instruction set, you can have reduced instruction set computers within multiple processors to try to increase the throughput by saying, all right, well, I'm going to have all of my division go through this processor, or I'm going to have all of my load and stores done by this particular processor. We're not going to really go into this in this course, but there's a more of a graduate level architecture concept called Tomasulo's algorithm, which how do you do floating point architectures, intermediate and regular calculations, each in their own processor flows, and how can you use that to improve the flow through of the program, and you can do something called out of order execution. That does work. All right, so 6.18, the three design goals for multiprocessor implementation are scalability. I want to be able to make it work no matter what on different machines, different processors, which of course, as you can imagine from running different types of multiprocessors, becomes a real coding challenge at the compiler level. Availability and power efficiency. So you will often have a difference here in instruction level parallelism and process level parallelism. So process level parallelism utilizes multiple processors by running independent programs simultaneously, which you can imagine if you're running a program that's supposed to do Word, you're running a program that's supposed to do EpicPen, you're running a program that's supposed to determine how the touch screen works, you're running a computer where I can type in words, I have the mouse, I'm typing in here. All of these are different programs, right? They're running them simultaneously on multiple cores to try to effectively use the throughput. And if you exceed the number of processors you can do to run the programs, that's when you start doing page swapping. So you can say, all right, I'm going to swap this page out to contain this program, swap in another program, run that, swap them back out, right? So process-level parallelism utilizes multiple processors by running independent programs simultaneously. Permits high throughput for independent jobs. And then a parallel processing program is a single program that runs on multiple processors simultaneously. So what happens when you have one huge program that can use 2 or more processors and you have multiple optimizations? That's why we use a parallel processing program. So I kind of alluded to how that works. You run different types of instructions on different processors. So for example, you could run branch and jump instructions on a one processor, and you could run R-type instructions on another processor. So that way, when you make the branch calculation, instead of having to do all the instructions where you have to do all the no-ops and flushing the program out, you can actually just go back to the previous instruction in the other data path and run it from there automatically. So instead of having to do all the stuff with the exception program counting, you can just bring it right back there. So we're going to be learning about branch prediction at the end of this section today. And so a multi-core microprocessor is a single integrated chip that contains multiple processors. So we kind of learned a little bit about that at the beginning of the course, how you can have multiple processors on multiple chips communicate with data buses. But in this case, a multi-core multiprocessor is actually going to have one chip where you're laying it all out here. And let's say each of these represents I'll just draw a quad core out. So you can actually draw it out like this, where it's on a single chip. So it goes through the entire synthesization process at once. So it allows you to run certain programs here, certain programs there. Or I can use both of these to run the same program to give my output. And so 6.22 is a really important concept, not just to see it on the exam. If you do anything involving coding for a job interview, MathWorks asked this question to me, Intel asked this question to me, Texas Instruments asked this question to me. Define and differentiate. Tell me the difference between ILP and TLP, which is what they're typically referred to as. Instruction level parallelism or thread level parallelism. So instruction level parallelism we've kind of talked about so far all throughout this course. Pipelining. Instruction level parallelism overlap the execution of the instructions to improve performance. So we have fetch, decode, execute, memory, write back for one instruction, right? So you see we have fetch, decode, execute, memory, and write back. Fetch, decode, execute, memory, and write back. So you have all this overlap in the instructions. ILP relies on hardware to discover and exploit parallelism dynamically. So in this case, the hardware is discovering that you can do fetch, decode, execution, memory, and write back in different stages. And if I'm not using that stage anymore, I can use that for the next instruction. So it's running the instructions in parallel, but they're slightly off, right? You have to worry about timing. You have to worry about control hazards, data hazards, and structural hazards. It also relies on software technology to find parallelism statically at compile time, which is kind of what you've worked on a little bit with the C to MIPS coding. Right? So you have some while loop, and you're trying to use an efficient coding, and you're trying to figure out, can I take advantage of multiple temporary registers? So that way, instead of having to wait for one, I can just run the next part. So I can calculate the pointer to the data memory to do my array, or I can calculate it to do my my pass by reference variable. It exploits implicit parallel operations within a loop or a straight line code segment. So you all have actually already done this. Up to this point, you have designed an instruction level parallelism application of an advanced digital system. Going forward, we're now going to talk about thread level parallelism, which is logically structured as separate threads of execution. So I do certain instructions at these stages, certain instructions in a different processor, different instructions in a different processor. For those of you who haven't taken operating system, a thread is going to be a specific set of code that's done by one processor, right? So if you ever look into an operating system's textbook, you'll see a processor kind of designed like as a block and of a little squiggle here to represent what's called a thread. But what that really is your actual assembly language program that's been compiled down from C, right? And sometimes you have to wait on this, and sometimes you have to wait on different registers. So we're going to be talking about centralized and distributed memory later today. But each of these is executing on its own. So thread-level parallelism is logically structured as separate threads of execution. Unlike instruction-level parallelism, thread-level parallelism is explicitly represented by the user by the use of multiple threads or of execution that are inherently parallel. So in C, Alex Gunter, you've coded in C? So how are threads invoked in P thread? That's correct. So basically in C, and you'll get to be familiar, you'll get your hands dirty with this when we're doing the Tensilica labs. So you would actually do a pound include P thread, and you would actually designate which programs or functions would be run in a specific thread, or which functions would be run in another thread, with the objective of improving the throughput. So that's where understanding how your code works at both the abstract level, where you're typically coding it, and the architectural level, and how do they communicate through the operating system and through the compiler, will really make you a very strong employee once you graduate. So one of the issues that always seems to come up is, well, if this was so great, why have we really been starting to do this recently, like since 2007? Computers have been around since the 80s, 70s, 60s, 50s, right? Like ones that are used by personal computers. So the first part is compiler design, implementation of parallel software. So this becomes a real issue. We now know that software must be designed to meet the instruction set architecture, right? We've learned this. I've said it ad nauseum, right? Writing a program that could be implemented in both sequential and parallel implementation is very difficult. Meaning, like, if you wrote a program at the assembler level, and you need to write a program that works both on single cycle, pipelined, and multiprocessor, right? You want to be able to install it on any machine. That sounds nasty, right? Caleb actually, yeah, it's a real problem, and people spent decades researching how to do it right, and it's still not very fun. Parallel software requires significant communications overhead and coordination. And two, cache coherence becomes a much larger challenge in the presence of multiprocessors, since multiple programs may be trying to access the same data simultaneously. So we'll go over this concept of cache coherence in a moment, but the idea of cache coherence is that if I have a variable in the cache, I have multiple levels of cache, right? So I have multiple levels of cache that are now being accessed by multiple processors. And let's say 2 or 3 of them are trying to access the same variable. Well, one of them adds, say the variable is u. One of them is adding u plus 1, or v plus 1 to get u. The other one's multiplying u by 2. The other one is taking that and storing into data memory. Well, we have to make sure that when each processor performs the operation, it has the most up-to-date and correct value of u. And so we're going to be talking about dictionary and snooping protocols today. And that's how you go about doing that. So there are 2 main concepts for cache coherence, and I did include my little Star Trek this time. Cache coherence is the consistency of shared resource data that ends up stored in multiple local caches. So we'll talk about the difference, you can see here at the bottom, centralized versus distributed memory. So make that look a little neater. So there's 2 main ways of implementing cache coherence: write through and write back. So write through, we define it here as you write to the cache and memory at the same time. Problem is it can be really slow, which you can imagine because you're updating each copy of the cache and the data memory. And as you learned from C to MIPS, that there's this difference between having to do load word and store word if you're passing by reference to a variable, right? As opposed to if you're using a local register, it just takes it out of the ALU, circumvents the data memory stage, and writes back immediately to the register. So you can see how that thing can be very slow. So you use a write buffer between the cache and memory to speed up access. And so if your store frequency is a lot less than 1 memory per write cycle, so you're not doing many writes at a time. And so write back is typically what's used more often. So write back is writing to the cache only, and you write the cache block to a memory during a page swap. So we learned about page swaps last lecture, right? So now this is where we have to coordinate. We're doing multiple processors, and we have to worry about pages, and we have to worry about the local copies of registers. So the local register updates. We need to make sure that all the copies that might be using for that register are up to date. So the register is going to write to the cache. So then what happens is once the page swap occurs, now that most up-to-date copy of the variable is in data memory. And so it reduces the memory bandwidth requirement, and I'm kind of alluding to what's going on here in 6.25, control can be complex. Yeah, does anybody have any questions on this so far? Yes, I think.
So what reason do you want to use write through instead of write back?
If you are aware of how slow, how like I won't use unoften because that's not a word, how infrequently you might be updating the cache. So if you have multiple processors and you're doing stores like once every 1,000 cycles, then you want to use write through because then you can update each copy in the cache and the data memory. And I'm going to talk about centralized and distributed memory here. What's going on is in some cases when you have multiple processors, each one has a local cache, and then you have an interconnection network where each one is using its own data memory. And so what would happen here is, let's say I'm doing a variable here, I update that, I update the cache, and then I would update the data memory here. And the reason why that becomes important is, let's say now this processor wants to use it, then I can go immediately to that memory, update my cache, and then perform all the operations. So that's when you would want to use write through. All right, so centralized versus distributed memory. So centralized memory is also a shared memory multiprocessor. Hold on. Just a second, if I have the right. Yeah. Okay, that is correct. All right, so centralized memory is also known as shared memory multiprocessor. I included that because you'll see SMP a lot when you're doing the 10 silica labs. So I want to make sure that you understand that centralized memory and SMP are the same thing. So you have these large caches right here. So in the diagram, they actually drew a little $sign, very punny. Single memory can satisfy memory demands of a small number of processors. So what's happening here is we have this memory network where the cache updates and then goes to the memory, right? And one of the reasons why I use write through for centralized memory is because of this little note that I have here about scaling beyond that is technically conceivable. What ends up happening is you have this one centralized memory that's dealing with, dozens or hundreds of processors. It becomes less attractive as the number of processors sharing centralized memory increases. So if you have like a dual core or a quad core, write through is the more attractive option. But if you're doing write back, that's when we want to do distributed memory in 8 cores or 16 cores, which is what's starting to show up in laptops. And Intel's already doing research in like 1024 core processors. So thinking back to the first day of lecture, what's one of the issues you think might happen with 1024 processors on a single chip? That's one, expensive. What about another thing? Yes, that's the other big thing. Putting on your lap, right? This one actually feels a little hot, and it's only like a quad. This one's a quad core. As it starts getting closer and closer, remember that diagram? If you see anything that Intel prepared, you will see that diagram. I've seen that diagram in approximately must have been 100 lectures at this point. Oh, that thing again. Let me guess, it goes to a hot plate and then the sun. All right, so 6.26, physically distributed memory processor. So in this case, the difference here is each one has its own localized memory. So using write back, you're doing all of these localized cache updates. And then when you need to do a swap, you update the data memory here. And then you perform the swap. So it's also cost effective. So if you're looking for low cost, this is the way to go. It's a cost-effective way to scale memory bandwidth if most accesses are to local memory. So it reduces the latency of local memory accesses, and communicating data between processors becomes more complex. So we're going to be talking about dictionary protocols and snooping. Or Snoopy bus or Snoop Doggy Dog bus, whatever helps you remember it on the exam. Communicating data between processors is more complex, which I just said, and must change software to take advantage of increased memory bandwidth. So we're working with C. We're starting to work with P threads. Each one of these threads that you're going to run is going to have, you're going to learn about this function a little later called Malloc, memory allocation. So you're going to actually allocate a certain amount of memory to a specific array. And so when you do that, when you allocate the memory, then when you root your pointer, the pointer is already pointing there. You can control where how much memory is allocated. The compiler won't be doing it for you. And if you're interested in fast, low overhead programming, since you're all electrical engineers, or most of you are electrical engineers, even if you're doing computer science, computer engineering, that's something you'd be very interested in. Does anybody have any? Yes.
What exactly is the interconnection network?
Okay, so the interconnect. Very good question. I believe that the next one is dictionary and snooping. Yep. I'm about to answer that question in a tremendous amount of detail. Any other questions? All right, so I've alluded to this cache coherence problem already. So here we have 3 different processors, and we have a shared memory multiprocessor with centralized memory. So we have the variable u. So in this case, we have u is 5 and u is 5. I update to u is 7, but let's say I want to do another operation immediately in processor 2. Well, I have one copy where u is 5, I have another copy where u is 5, and I have u is 7 over here. So how do I do that? Well, I need to take advantage of this interconnection network, which is just a bus, very similar to your bus between ALU and data memory, or ALU back to write back. So you're going to be using this bus to have a number of interconnections between each processor and the data memory. And so the processor actually has, the interconnection has its own protocol for determining which information gets sent where when. So you have to, which operation is going to put u on the bus first. So in this case, what we'd want to do is we'd want to say, well, put u on the bus, and then we have to use our oversight protocol to say, hey, which other processors are using variable u at this moment? And they'll say, oh, wait, both of them are. And it'll say, all right, hold on. Before you do anything else, let me update this processor, right? Then it updates it to 7, and then it does its operation, and then it's doing the correct value. So maintaining that, that's what cache coherence is. So processors see different values for u after event 3. With write-back caches, values written to the memory depends on the happenstance. I must have worn a top hat and a monocle when I wrote that note. When the cache flushes or write-backs to the data memory. So with write-back, we have to take advantage of cache coherency and cache consistency. And in order to do that, we have dictionary-based coherence and snooping along the interconnection bus. So what's going on with dictionary? And then, see, I told you an answer to your question was coming, Jacob. That's everything going on your interconnection bus. So dictionary-based coherence. We define it as utilizing existing cache hardware, like the invalid bit, to maintain cache consistency. This approach allows the state of the coherence and consistency to be more distributed. So basically what's going on here is that we have all of these different processors and directories right next to the memory. So this diagram, it says memory, I/O. So we have I/O buses and the directory. So the directory is telling me what variables are being used in each memory and cache, right? So let's think about our cache consistency problem that we were talking about earlier. We had U is updated in this cache. It goes here. Ignore that. It says, all right, now I've updated this. Now what's going to happen is the interconnection network is going to use the consistency across all of these, and that's what snooping is. It's going to go to these directories and say, do you have U? Do you have U? Do you have U? And this one goes, yes, I do. Then we update that value in the cache so that way it can use the most up-to-date value. And so how that's actually, so this approach allows the state of cache coherence to be more distributed, as shown in the diagram below, but introduces higher delay as CPUs must request that a bus, like the Snoopy bus, has not yet updated. So the Snoopy bus protocol can ensure consistency across the caches. So that's what's actually, it's snooping on each one. It's kind of like you have a weird neighbor, creepy neighbor, making sure everybody, does whatever. It works by monitoring or snooping the different caches and overseeing what operations the processors perform on the data. So that just formally describes what I was describing earlier. So this interconnection network is connecting all of the different processors. And we have, this is a distributed memory model. And each one has a directory. By doing write back, we can actually take advantage of this directory protocol. Otherwise, we'd have to write to only one memory. So in this case, we use the directory. When it updates, it checks to see if anybody is actually using it. If so, it updates their version of that variable, so that way we don't have an instance where the cache coherency is screwed up. Does anybody have any questions about this? All right. All right, so ignore that because this is different lecture. All right, so I've alluded to in previous lectures this concept of branch prediction, right? So when we talk about it very briefly in pipelining, we say, all right, we have a branch that we've calculated, and we don't know if we're going to calculate the next one or going to be going to a different instruction. So in that case, it's very simple. We just flush out the data path by sending a bunch of control signals through zeros, flushes it out, and that's fine. But when you have multiple processors and you're calculating a branch, you need to jump past a number of instructions that are not in that one processor. Well, what happens if I have an updated value in the other processor that needs to use this? Or we have a case where, and this is where it's going to be even more common, if I is equal to j, right? So we now know that we rely on the values in the registers, which may be updated in the program. So if you were in pipelining, you have to worry about whether or not somebody actually put it in as a fscanf value, and then it's updated, so you can't guarantee which one's going to be bigger. But let's say I'm doing this in one processor, and the other processor is running I++. So I have an instance where I get to this instruction first in the first processor, but I know that I need to do I++ in the other processor before I can branch. Well, if I haven't got there, then I would just be inserting stall, right? But let's say I don't want to do that because I want to try to make the program run faster. So what I want to do is actually try to predict what I'm going to branch. And so a branch is a digital circuit that attempts to guess the result of a branch instruction before the instruction is executed and the required information for the branch is known. So we take a guess. So there's a whole process of guessing. And that ties in because we have to wait from the cache, from the distributed memory for the directory protocol and the snooping to indicate what that value is going to be, update the value, and then run it. But if we guess, and let's say we're doing a while loop where we loop 100 times, right? That means we're going to meet the condition 99 times and then break it the 100th time. So we can potentially predict, now very high accuracy, what that branch is going to be. And so here, this example, I kind of just told you the exact same thing, but basically you don't know what it's going to be, but we have to wait on the value of I, right? And so there are two types of branch prediction, static and dynamic. And then, so static branch prediction is what happens when we use information that was gathered before the execution of the program. So we have some sort of, as we're compiling the program, we start out and figure out that more than likely we're going to be branching a certain percentage of the time. There are actually known benchmarks that you can use. There's a whole field of study in that. For the purposes of this course, all you need to know is that as the compiler is going through a program, it can make a best educated guess and run it with a certain percentage of accuracy. And usually you can get it, so if you're doing it really well, you can get it to 80 to 85%. And so dynamic branch prediction uses information about taken or not taken branches gathered at runtime to predict the outcome of the branch. And so we're going to do an example problem here in a moment that describes precisely how that's done. And so the general, there's 8 or 9 different ways to do branch prediction that are more complicated. We're going to study a method called 2-bit branch prediction. And so the whole idea is that you're maintaining a branch prediction buffer or branch history table recording the last behavior of the branch, small memory buffers indexed by the two least significant of the branch instruction address. So what happens is if you generate an address, right, in the immediate value of the instruction, you use the 2 least significant bits of the branch address to calculate whether or not you're going to do a taken or not taken. And there's a finite state machine that we're going to cover up next here that actually shows you, like, if you start here, where should you go for the next branch prediction? So did we take the branch or did we not take the branch? If we took it, we'll go to another state in the FSM. And then if you know the finite state machine, you can actually figure out for a given set of taken and not correct guesses whether or not we're actually going to continue branching or not. Does anybody have any questions about this before I go to the diagram? So this is actually so this is the end of 6.29, so scrolling up here is fine. So this is the actual finite state machine. So if we start out at a particular state, and the example problem we have here is actually going to start out at n star. So we have n star means that if it's n or n star t, we're going to predict that we're not going to take the branch. Meaning that if it's I equals j, we are predicting that I does in fact equal j. So if we start here, let's say we predict the branch is not taken, and then we get the updated value, and we were supposed to take the branch. So here's what's going to happen. We would actually, if it's taken, which is the t value here, then we would actually go to n star t. And the reason why it's, remember that the 2-bit branch prediction, you have 0, 0, 0, 1, 1, 0, and 1, 1. Each of these represents a particular state. So we would start out at the loop with a branch address. If it's 1, 0, well, we're going to predict taken. So that's how you use that static and dynamic branch prediction to kind of calculate what's going on. So in this case, let's say we guess wrong again and it's taken twice. Well, then we go here. Right? Now we're at predict taken, so then we predict taken, we stick in that state until we're supposed to predict a taken and then it's not taken. Meaning in that case, we actually broke it, I didn't equal j. Well, now we're at t star n. And so forth. Does that make sense? It's pretty straightforward. So what I'd like to do, I'm going to work through this problem together. So in this case, we're given a 2-bit branch prediction method with initial state of n star and the following set of branches, meaning that we didn't take it, we didn't take it, we took it, not taken, not taken, taken, not taken, not taken. Make sense? So we're actually going to work through here and see where we're going to end up. So if we are starting out, we're starting out at n star, right? And we don't, and we end up, so we're predicting that we're not going to take the branch. So we predicted n. And where do we actually end up? N star, correct? Because we actually just go back here. And it's the same thing here. So then we end up taking it, right? Meaning that we guessed not taken. The reason why is we're still at n star. So we actually predicted no, but then where are we going to end up now? Because we're actually taking this branch. N star t. So then we take the branch, we predict t. I'm sorry, we predict n because we're still in n star t, correct? So we predict n. So now where are we going to end up? T star. So we predict not taken. I'm sorry, we predict taken. I should go through. So we predict taken. It's not taken. So where do we end up? T star n. Very good. Here again. Now we're going to predict t. We still predict taken, but we're not doing it. So now we end up in n star. See how this works? If you know the finite state machine, you can just follow along with it. And here we're going to guess n. It's taken, so we end up in n star t. We predict n. We guess n. But since we were in n star t and we're n, now we go to n star. Likewise, we predict n, and we still end up in n star. See how that works? And so this is a fairly reflective problem of what is actually happening. Because branch not taken means we're actually doing the code inside the loop, and then we do the jump back up to, like from the problem we did in the quiz. We're actually jumping back up to 256. We're predicting, and we'll keep doing this. And so without going into too much detail, because I feel it's a concept that's a little outside the scope of the class, and for those of you still writing it down, I'll go back and do the diagram there. Well, what happens when we have to make a change and guess wrong? Well, what's going to happen is we actually go back to that instruction and then start redoing the instruction. But it only happens every once in a while. If you're guessing it 80% of the time, then you're getting an 80% improvement of throughput. So by the time you actually get that, not only have we guessed properly, we've done all the code inside of the instruction. So you've significantly improved the performance 80% of the time. No. Does anybody have any? Yes.
Is there a consequence for predicting wrong?
Basically just what I said, that you have to kind of step backwards and then re-execute with the new information.
How does it know if it predicted wrong?
Because what's going to happen is, okay, so this is a very good question. So if it's going through the loop, right? So if I equals j, and I guess predict branch not taken, which means I'm going to go in the loop and I'm going to start executing the code. So then I start saving the results of these registers. And what's going to end up happening is the directory is going to update I in a different processor. The Snoopy bus is going to say I have a loop going on here in this processor. I bring it over, I update the value, and then I check to see if it was correctly taken or not. If I guessed correctly, then it just goes on to the next loop without stopping. If it doesn't, what's going to happen is it's going to say, wait a minute, wrong, try again. And so what's going to happen is we're going to go back up, we're going to get the new value of I, and then we're going to do a branch. Does that make going into the hardware that does this is actually like probably a day-long lecture, and it's a little more of a graduate level concept. But that's generally how it's done. Does that answer your question? Yeah. Awesome. Any other questions? Cool. So, multi-threading. Yes. Let me see if I can zoom in out here so that way I can get the whole TGO on one screen. So, 4.30. So we were talking about this concept of we're doing multiple threads running the same program, or trying to figure out how to do certain instructions, right? So there are actually multiple ways to do multi-threading. So this is where doing the compiler level and knowing what's actually going on in your program becomes useful. So multi-threading involves performing multiple threads of execution in parallel. And by doing that, by using these different processors, you're able to replicate registers, the program counter, because you have different program counters for each process, and then fast switching between the threads. So once you actually get done and you're able to execute the specific code, you can use the write back in order to maintain cache consistency, doing page swaps to do different parts of the program, or being able to just run the program really fast. So there's two approaches to this. Three. Fine-grained multi-threading is what happens when we switch threads after each cycle. And so I have a little, and just to give you a preview, I have a little diagram right here where I'm going to describe what this all means. So switching threads after each cycle, we interleave instruction execution, meaning that we're going to be doing different instructions in different processors by interleaving them. And if one thread stalls, meaning that we have some sort of stall based on we have an instance where the compiler has issued a bad opcode or an arithmetic overflow, then others are being executed. So we're taking advantage of a stall by executing the other instructions while we're waiting on it. And then coarse-grained multi-threading is only a switch on a long stall, meaning that we have some sort of level 2 cache miss. So remember from average memory access time, we had a level 1 cache miss and we were able to get it quickly. But if we have to go to the second level, then would actually do this coarse grain multi-threading. And it simplifies the hardware that used to do the overhead for the switching, but it doesn't hide shorter stalls. So the whole goal of fine-grained multi-threading is the moment we get a stall, we want to immediately be running another instruction, right? But what ends up happening is if we have coarse grain, well, we get a stall, it still stalls. Okay, now we should switch. And then this last part is simultaneous multi-threading, which you'll often see abbreviated. You don't have to write this in the TGO, but you'll often see this abbreviated as SMT, right? So simultaneous multi-threading is what happens when we have a multiple issue dynamically scheduled processor. So this is where I'm issuing multiple instructions simultaneously, and for a dynamically scheduled processor, meaning that I'm going to be scheduling it based on the needs of the processor and the needs of the program. So if I know that a certain processor is not being used very often, I can dynamically switch that over and say, all right, well now that I have a processor that I've devoted solely to multiplication problems, well, I don't have any more multiplication problems, and I still have a large part of the program to do, right? So now I can dynamically allocate another type of instruction to that processor, which would allow me to continue to improve the throughput. So it schedules instructions from multiple threads, and the instructions from independent threads execute while function units are available. So that's what I mean by this function unit is just a fancy way of saying that we try to have different processes do different types of instructions. And then within threads, dependencies are handled by scheduling and register renaming. So while we're not really, we might go, actually we're going to go into register renaming in the cadence part. So just for the time being, just know that when you're doing loops, if you are trying to figure out which loop you want to use and you're trying to do this, there's this process called loop unrolling. So if you had just I equals j, and then we have some sort of variable, and I++ is one of them, and then we'd have to do a calculation here. So what's going to end up happening is we want to, if we can optimize the code, we can actually, instead of, let's say compiled down, it takes 15 instructions. So each loop would take 15, right? Well, let's say I can optimize it so it's now 10, 10, 10, and 10. So now I'm doing it in 30 instead of 45. So I can unroll the loop to continue doing certain instructions while I'm waiting on the next branch. So if I'm able to calculate how long it'll take, I can say, well, just add 4 to j, and that'll break the loop, and then I just do it 4 times of the execution. So the compiler does that. I think it's a little outside the scope of the course. And you can start telling we're getting to the end of the conventional advanced digital system because I'm starting to say outside the scope of the course a lot. But the general idea is that you have this scheduling and register renaming, and you're able to optimize your loop. So in Tensilica, there's this concept called flicks. And so what they want to do is they want to do this register renaming by doing a very large instruction word. So if you have 3 instructions, like so, what they want to do is take advantage of the multiprocessing, and they'll have this flicks instruction, which will do 3 simultaneously. And then they'll rename the registers in order to just be able to get it out on the output really fast. Any other questions on this? So what does this all look like? All right, so this is your concept of, you have 4 different threads here, and this is how coarse fine and simultaneous multi-threading actually solve this problem. So if it's coarse, what's actually happening is it gets here, and then it gets to this level 2 cache miss, right? And then it goes, oh, okay, well, now that I'm done, next thing I'm going to do is I'm going to allocate the processor to do thread B. So it starts out with this correlates to that. And I have a level 2 cache miss. And instead of waiting on this longer cache, I start doing thread B to kind of improve the throughput. So for fine grain, remember how we defined fine grain as we switch every clock cycle? So if you look here, this 2 part corresponds to this guy, right? And then this 3 bit here is the first clock cycle of thread B. And then this gray is thread C, and so on. See how this little white one here is, this little light gray one is there. You see how it works every cycle? So now it's doing more calculations, but it can be done even faster. So using this simultaneous multi-threading, or SMT, we can dynamically allocate it. So what's going to happen is I can say, well, I have 4 processors, so the first thing I'm going to do is going to be the first 2 of A, and then I'm going to do the first 2 of B in the first cycle. Well, the next one I still have a third one of B, and then I got 3 from thread C. I'll use that. And then the next cycle, I have this 1 thread from D, and then I use the second cycle of A, and then the 2 from B. So you see how that's working, how it's dynamically allocating them to try to optimize. And as you can probably imagine from everything that you've learned today, that when you're doing the simultaneous multi-threading, and if you have variables being used by multiple threads, doing this all at the same time is where you start really needing your cache coherency, your dictionaries, and your snooping buses, right? Whereas if you do it like this, it's nowhere near as complicated, of course. So the trade-offs are cost, and here you're also having to worry about hazards. And you can see actually here, I was going to go into something, and this is a really good example. Here, sometimes you're still going to have stalls if you just don't have anything you're waiting on, right? So here in this case, threads C and D are done, and then we still have to wait on the next cycle in order to do 4, right? All right, so the last concept we'll cover in section 6 is this idea of single issue multiple data versus multiple issue multiple data. And so what's going on here? We have single issue multiple data in the table. And you can actually configure the Tensilica processor to do both of these. It's actually the tool that you're going to use is actually really cool because it'll allow you to actually get to play with the processor and see how it actually, all the instructions actually flow through. Can you do it in pipelining? It actually has a little pipelining diagram that I can show you. So the program, single issue multiple data, well, there's 1 copy stored in memory of the data. Or in multiple issue multiple data, each processor has its own copy. So we had the distributed memory, right? Because that's more of a multiple issue multiple data type concept. So the operation. The processor operates synchronously on 1 program. And the multiple issue multiple data, the processor acts asynchronously on multiple programs, but processors can be used like SIMD. Meaning that you can either use the processors to do multiple data, or you can actually have the processors do, multiple programs, or you can actually have the multiple processors run the same program. So it's kind of the idea of thread level and instruction level parallelism. So the instruction decoding, 1 instruction decoder in the control unit, just like you have in MIPS. And then in multiple issue multiple data, each processor contains its own instruction decoder. So that means each one contains its own instruction memory. So each processor is going to have its own instruction memory and data memory and controller. So loop handling. Yeah, you know enough to do that. For 1 control unit handles increment and decrement of variables, while each processor does computation. So you remember how you're doing branch computations in the ALU to calculate the 0 bit to then determine the branch address. So in single issue multiple data, 1 control unit handles increments and decrements while the processor does the computations. The execution of branch statements and jump statements are serialized. Whereas in multiple issue multiple data, It's kind of this thread level type parallelism. Each processor increments, compares, and computes. So you want to try to have a good control of what processor is doing what branching and what jumping. For conditionals, there should be a comma there. For conditionals, each processor acts as though it's a uniprocessor. So each processor it's doing its own set of looping. And then the last thing, the interprocessor communication, which is where you have your bus, interconnection bus. The communication operations are automatically synchronized, whereas if you're doing multiple issue, multiple data, and you're trying to do this throughput, you require more overhead. So you need this explicit synchronization and identification protocols. So just like everything else, you start adding performance, you require more hardware and software overhead, which of course incurs cost. So does anybody have any questions on this? That's the exact opposite of what I wanted to happen there. All right, so, now people are starting to Exam 2 review. So the take-home portion is already posted on Blackboard, and it will automatically become available to you at 11 o'clock. I will post this video on Blackboard, not on Blackboard, on YouTube, and it's the same kind of concept. I found another job at Texas Instruments where actually it was really convenient because it tries to emphasize multiprocessing in the job description, so you can kind of use what you've learned since exam 1 to tailor your resume. Generally, I want you to try to, just like before, I want you to tailor your resume to the job description. And for those of you who might try to be lazy and just try to reprint it, if I had requested you to do something before, next time it'll cost you a lot more points. So if you think I'm not going to notice, I'll just grade it the same way, and it'll cost you a little more. So. But remember, the whole point is you're supposed to get experience with actually preparing for a job interview. So I think that's pretty cool. But wish my professors did that for me. What do you think will be on the exam? Pipelining? Okay, so that's one thing. What specifically about pipelining? Okay, can you speak? Okay, so that's single cycle. So in pipelining, what might be there from pipelining? Okay, so hazards, so define hazards. And what else? Identify hazards. So remember that 3-part problem where you had like hazard, 4 instructions, and then you had to identify where are the hazards, identify them, like you said, as well as what happens when there's how do you insert stalls, with no forwarding. Fairwinds, which I think is something from Lord of the Rings. And then what happens with forwarding, right? So define hazard and define and describe the 3 types, right? So you got single cycle and pipelining. What else could I ask you about?
C to MIPS.
Yep. C to MIPS. It can give you a loop. It would be similar to the last problem. Remember how I had you guys do an example problem? No, 4 instructions in the, I give you 4 MIPS instructions that like load word at like that one example. and there's the 3 parts where I said, tell me where identify the hazards, then without data forwarding, insert stalls to make it work, and then the part C was identify the hazards if I have data forwarding. So yes, I will limit. I will not ask a problem that requires more than 4 instructions. And so the loop problem. So what else could I ask you about? So if I go into Blackboard here. So a lot of the, so you probably figured out from doing exam 1 that I try to have this actually serve as part of a study guide. Creepy clown sightings prompt Ronald McDonald to go into hiding. Okay. Okay. There we go. So it'll come available in 19 minutes, but it's content. Oh, okay, there it is. Let me move. I can move it up here. All right, so all right, so a lot of stuff. Define pointer. So what kind of thing? So you got that C to MIPS, right? I'm going to probably ask you something where I'm going to have the arrays and the int star sum. Describe how Ritchie and Thompson invented C. Procedural and object-oriented programming language. Define the truth table for single cycle MIPS data path. Full single cycle for R-type, I-type, and J-type. Basic concepts of pipelining. Define pipeline hazard and state and define the 3 types of pipeline hazards to give an example of each. Oh, hey, look at that. Looks familiar. Define data forwarding, and pipeline install. So you understand those. You should be able to complete that problem, right? Here's another one. Assuming n computations, k stages for an ideal. I'll expect you to be able to do that on the exam. Ideal pipeline. What else? So I got C to MIPS. So describe the process of handling an exception. So what else? You all tell me. Yes?
Drawing a data path.
Okay, so that is a single cycle reduced data path. Yep, so specifically about it. So I want to do, I would probably say, remember I told you to differentiate between TLP and ILP. I'd also, I would ask you to draw the 2-bit branch prediction scheme and do show the actual, so just like the example problem. And then this last one, describe multi-threading and differentiate between coarse, fine, and SMT. This will be on Blackboard, just taking photos as it looks tacky. More importantly, you'll probably have professors freak out like that because there are a lot of things, like especially, by the way, let me warn you, when we do the cadence, don't do any of that taking photos of it because you'll see on the videos and everything, it says cadence confidential. When you go into industry, you'll be expected to keep industry secrets, or if you go work for the government, you'll be expected to be classified information. So I'm just developing a good habit. So at the same time, like I'm posting this in 5 minutes. I gotta kill you. So let's see, anything else here? Oh yeah, I'll 14 or 15. One of these two will be on the exam. The reason I say one of the two is because I typically find that I'm trying to, since I'm limited to 75 minutes of asking. So either the virtual memory translation process or state the process once the operating system determines a page fault has occurred. So your exam will be some subset of this, the in-class portion. And if you go through these and do all these and study it and see how it contributes to that, you should do very well on the exam. All right, so on that note, it is 10:45. Does anybody have any other questions? All right. Take-home portion is due on Tuesday. On Tuesday, we're going to be starting out. I'm going to be showing you how the cadence tools work and what I'm expecting from you. On Thursday will be the in-class portion of the exam. Yes, hi. Yeah, TGO. Don't worry about these TGOs because you're already doing a take-home portion of the exam. So don't worry about TGOs. Just do take-home portion. That'll make the TA happy as well. Yeah. So you'll actually see that these are word for word. I'll email all that out. Yeah, we'll just work on it like normal. It'll take you as before. Just go to the lab and we work on it today.
So when somebody call you, put any notes on them, but they just hand it the same thing.
No, tailor it to the specific job. Yes. Yes. I handed back them all. You might. These are all the ones that I have.